Welcome to the course Gear and Gear Unit Design, Theory and Practice. Now, this is the first lecture of module 1 and this means the first lecture of the first week. This module 1 is on Introduction to Gear and Gear Unit Design and the first lecture is on Introduction, Motivation and Theme of the course. In this lecture, I shall give a brief history of tooth gear invention and development, and next something about the gear train, then special sophisticated gearing, some important information. Now, coming to the history of tooth gear invention and development. Now, to transmit the torque, to magnify torque and to reduce the speed, from the very beginning of the human civilization, people were started thinking how it can be done, and they used various methods, lever, then rope tackle, etc. And in that way also tooth gear came in the way. Before that, of course, the friction drive was there and some sort of wheel drive was also there. However, early example of tooth gears date back to the 4th century and 4th century BC, before Christ, and it is in China. Now, first tooth gear was somewhat what I am showing here. Of course, this is not the first tooth gear that was introduced in long back, and probably that was used for mechanism, but this one is an example where it is transmitting also the torque. Now, this is hand lever driven pinion and gear with winch drum to lift water from below ground level to first floor in a castle in Poland, and based of the information, it is built in 15th century. Now, if we look a close look to the gear and pinion, as you find this pinion is few cylindrical wooden rod connected by two piece of circular wooden blank, and that is pivoted on two wooden column, and that is driving the teeth, which is also made of wood, and this is also put on a rim, wooden rim. This can be splitted, somewhere it can be splitted and bolted. Okay. So, these are simply press-fitted over there, and that teeth looks somewhat like involute, and this is the drum, and this is a hole on the top floor, and the water well is just below this, and it is in the ground floor and in a well. Next, if we look into this gear, this is probably the first set of gear unit now discarded to drive the cable car in Lausanne, Switzerland. This tooth looks like involute. However, this is apparently looks the involute like tooth, but with slight an undercut here. If we notice this part, say it is looking slightly undercut, but later we will learn for this number of teeth undercut was not necessary, and probably to give more clearances, this tooth shape looks like that, but it is very close to involute. And these gears was initially cast this with this tooth form, and then probably this was also milled to get the shape. Next, tooth profile particularly of gear looks like close to involute, and this is, as already told, cast and mill gear. In after introducing the tooth gear, there is a lot of development on the gears in China, and they also introduced the differential gear mechanism. Also, it is found in China for a device which is called south pointing chariot, and this was also around it is before Christ, but after the development of the tooth gear. Now, as you see in this figure, that a man is pointing his hand and he is standing on a chariot. Now, if this is put pointing south, and then if this wheel are rotated or dragged, pulled in some direction, this finger will always point to the south, and it became possible with the here a gear arrangement, which is the first differential gearing arrangement. Of course, one thing we should consider, that this wheel, it should not slip on the ground, they should firmly attached on the ground and they should roll. Now, if we look details of this gearing, as you find that when the wheel is rotating, these wheels are rotating these gears, two gears, and then here as you find this gear is rotating this one, and in turns it is rotating this column, and on that column this man is standing. So, whatever may be the rotations, this will always point towards the initial point. In this case, it is always pointing toward the south. That means, whole device we have to keep directing this finger toward the south, and then it would work. Now, here if we look into these gears, this is again on the simply on cylindrical bar put on cylindrical wooden disc. Now, this is by no means the present gear tooth form, involute or cycloidal. It is simply pin type gears, but close observation will give us that this is perhaps the first idea not only of the differential, but also of the bevel gear. Say if we look into this gear, particularly this gearing, see this is the concept of bevel gear. Next, if we come to the bevel gear, as you see here, this is a differential unit which is used in automobiles. These are hypoid gears here, and this is the differential pinions, and then this it is driving the two wheels, but when it is turning, then one will be with high torque and it will be almost off, another one will rotate in a angular directions. Now, coming to the bevel gear, this bevel gear developed eventually with other gears, but there are different type of bevel gears, and it is first it was needed to drive in intersecting shafts somewhat in the 90 degree. Now, if we look into the bevel gear performance operation, then we will see that from bevel gear with angular change, features change, it will come into worm gear. So, now here what it is shown, that is a straight bevel gear, but it is of course the intersecting, if we consider the axis through the pinion and axis through the gear, they will intersect, but looking into this photographic view, this is of course not 90 degree, this angle will be slightly more than 90 degree, but that can be achieved by straight bevel. It is called straight bevel. When we learn about more about the bevel gears, then we will see this what is straight and what is helical, etc. Now, next on the bevel gear, if we look into this, this is spiral bevel. The spiral bevel means the same, it might be the same intersecting shafts, same teeth number, but tooth are spiral, and if we consider the center of curvature, that is somewhere outside this gear teeth, okay. But still the shafts are intersecting, maybe 90 degree or maybe more than 90 degree. So, this is spiral bevel, it is close to the helical gear. Now, if we consider this here also teeth are some sort of the spiral, but this is, you can say that it is somewhat helicoid, and in this case we can shift the shaft also, and that this means that the axis is not intersecting. Now, this is example of herringbone bevel, or you can say double bevel, double teeth bevel, and in this case as you see that this pinion will experience, or vice versa, the gear will experience the force both in this direction and in this directions. Therefore, this you can say the axial force towards the shaft is neutralized, but this is expensive and also this is not normally used. Now, next if we come to this somewhat non-parallel shafts, then the first example is the crossed helical gear. The gears, what we normally, if we say gear, it is spur gears, it might be straight tooth or helical. Here what it is shown, this is a crossed helical gear, that means shaft you can cross, and then it is shown that here this in the photographic view it is 90 degree crossed helical, and when this rotates then this will also rotate. Okay. Now, the further if we develop this one, that is the crossed helical gear, then we shall arrive into worm gear. Now, in case of crossed helical gear, the teeth number of this one and teeth number of this, I mean particularly teeth number of pinion may be 3, 4, 5 etc. Whereas, in case of worm gear, a self locking worm gear will have only single start spiral teeth. This is, as you see, that this is like a thread, even if it might be 3 teeth, that within 3 start, but this will be always in spiral form, whereas in this case these are not fully spiral, it is something like helix gear. So, this is, you can say, a transformation from bevel to worm, and this is all are non-parallel shafts. It might be intersecting or might not be intersecting. Now, here it is perhaps we should know, particularly bevel gears, they are of various type. The straight bevel gear, which I have shown in earlier slide, it has the conical pitch surface, teeth are tapered, but straight and cone tapering towards vertex. Spiral bevel gears have curved teeth at an angle, resulting in tooth contact to be gradual and smooth like helical spur gear. Hypoid bevel gears are similar to spiral bevel gear, but the pitch surfaces are hyperbolic and not conical. Pinion can be placed or offset, and hypoid bevel gears have the highest tooth carrying capacity of same size in comparison to spiral bevel gears and straight bevel gears. Now, apart from that, there is another class of gears which is zero bevel gears. It is something like a straight bevel gears, but tooth are curved like spiral bevel gears, but that curvature not in the not an angle. This is the center of curvature, or maybe the center only will be somewhat straight on the teeth. Now, apart from that, usually for bevel gear another term is used which is called meter gears. This is used mostly for motion transmission, and this is of ratio 1:1. Now, the worm gear was invented in the Indian subcontinent for use in cotton jeans sometime during 13th and 14th centuries. This is a picture from Encyclopedia Britannica, and where it is shown that this is the cotton jeans. Cotton jeans means the raw cotton will be put one side, and this will pass through this, and while it is passing, then the seeds will be out of the cotton, which is shown here. The seeds are coming out. Now, this is as we see, this is a spiral one, and this all projected pointer can be considered as if the circular teeth of circular gear, and when the cotton passes through this, the seeds comes out. Now, this is the first example of worm gear, and if we look into the worm gear, this is of course from a internet, and this is showing that how the worm gear operates. Now, however, in this course we shall, although we shall learn little bit about bevel gear, worm gear, etc., design of that, but our the design method, etc., mainly we will concentrate on spur gear, helical bevel gear, helical spur or straight tooth spur gear. Okay. Now, this is a figure, it is showing that a common spur gear unit of simple gear chain. Now, if we look into the industrial gearboxes, it looks somewhat like here, which I have shown in a photographic view. This is general purpose helical gear reaction gear unit. Here we have shown it is 2 stage, and when the power is transmitted in the first stage, then through the pinion to the next stage, this is called compound gearing. So, we have the compound gearing. If the reduction is more than single stage, then it is compound gearing. And if we look into the top open assembled view in drawing form, it will look somewhat like this. which is shown at the middle. Now, we shall in this course, a major portion of this course is devoted on designing such a gear unit. Finally, we will see a rack and pinion. A rack is nothing but a gear which is having infinite radius, and in involute, in case of involute, here teeth profiles are a straight line inclined at an angle of the pressure angle of the gear. Now, internal gearing. The tooth also can be generated inside the ring here, if you look into here, and then power can be transmitted. Either the pinion can directly engaged with the internal gear, or through an idler we can have the simple gear train, we can have also compound gear train. Now, it will be epicyclic gear drive. Epicyclic gear drive or planetary gear drive, these are the planets. These three pinions are called planets. So, planetary turn is due to the following the motion of the planets. So, it rotates about its own axis as well as rotates about another central axis, and it is also called epicyclic gearing. And in that case, for reduction, speed reduction, usually we will find the internal gear, that is the ring gear, will remain fixed, sun will be input, and a planet carrier, that will be the output. Now, if we look into this view, here the internal gear, ring gear is fixed, and then this is the planet carrier which is the output, and the sun is the input. So, we will get some extra reduction than the simple gear ratio, that will come later. Now, this is of course the simple gear train, and here this planet is, and you can say some sort of idler. It is not transmitting the torque, the gear itself is not transmitting the torque to the shaft, it is transmitting torque from the sun to ring gear. Okay. Now, it can also be made, this epicyclic gearing can also be made compound. In that case, what we find, this sun gear is connected to a somewhat larger planet gear, and this planet gear or pinion is integral with another small pinion, and that is connected to the ring gear. The ring gear is kept fixed, and planet carrier is it is passing through this planet gear set. Okay. So, here these are by no means the idler, because this is transmitting torque from here to its adjacent pinion. So, this is compound epicyclic gear, this is simple gear train epicyclic gear with internal gearing. The same epicyclic gearing can also be done with external tooth. In due course, we shall learn a little bit about that also. Now, then I shall discuss about some very special gear. In this special gear, what we find, the outer ring gear is fixed, and a inner pinion, it is moving. Apparently, it is flexible. Yes, it is a flexible gear, and here the tooth difference is only 2, and we get the reduction in the order of the tooth number of the ring gear divided by 2, or tooth number of the pinion divided by 2 depending on which one is fixed. Fixed mean rotation of it its is about its own axis is restricted. Okay. So, depending on that, and this is called harmonic drive. With more or less similar motion, we will also find the Wankel engine. In case of Wankel engine, of course, the tooth are not like in volute, which is possible with in harmonic drive. This is called cycloidal teeth, and this is also a gearing action. And if we come next to another machine where we have distinct teeth, in this case we have 7 pin outside and 6 lobe profile inside. The inner one is called star, outer one is called ring. Now, this also can be run at in epicyclic manner, and particularly the unit which I am showing, that is used as hydraulic motor, very high torque low speed or low torque low speed high torque machine. If we look into this, their motion, then it moves something in this manner, the star is moving in this manner. Now, particular this machine is that the oil is pumped into the chambers which is formed by this contact, and then this started rotating. The output is taken through a cardan shaft from the star. Okay. But if we consider these are also the teeth, gear teeth, this is a class of cycloidal teeth which is called epitrochoidal. This profile is modified epitrochoidal, and these pins are envelope of that. Envelope means it is conjugate to this one. So, this gives also the gearing motion, and with the same profiles, that is epitrochoidal profiles, the gear unit is also available, which is called cycloid speed reducer. As you see here, this is the epitrochoidal star, and these are the lobes in the envelope, which is essentially circular, and the planet this is the input, this is a cam sort of thing, eccentric cam, and the output is taken through these holes with the planet carrier. The planet carrier is this one, this is the planet carrier, this is the lobe of the ring, this is the planet carrier, this is put inside. The axis of the input shaft and axis of the output shaft will be in the same directions, and these pin size and this hole size differ by the eccentricity, or which is the center distance between that. So, this will have two motion, one is rotation about its own axis and another is revolving around the central axis like this one, and this, as I have already mentioned, this is called cycloid speed reducer. Now, if we look into the manufacturing process of processing, then first of all the blanks of the gears can be readily cut from a stock, or it can be forged, it can also be cast. After casting, then we have to go for hobbing, and if we think of the strength of the material with respect to heat treatment, hobbing is possible up to certain hardness. So, sometimes the blank is raised to that hardness and then it is hobbing. So, here it is shown that hobbing of a helical gear. This is the helical gear and this is the cutter. This is helical gear and this is the cutter. This cutter is like a thread sort of things, and with a cut here to relieve the materials, and while this is set, the hub cutter is set an angle that is calculated from the angle of the helix and the lead of the or you can say yes, the lead angle of the hub cutter. Okay. So, that is a different subject, manufacturing, but still I have shown here how the hobbing is done, and this hobbing is also possible to generate or make the state spur gear. This is the state spur gear. So, the hub is set in such a way considering the angle of helix is equal to 0. Next comes the shaping. If we think of the shaping and hobbing process, these are called the generation of teeth. It is not exactly milling, it is generating the teeth by cutting process. Here this hub rotates as well as the blank also rotates, and then hub gradually come down and goes up while it is cutting this material. In case of shaping, the process is that a tool that will move up and down as well as it will rotate and it will generate the gear. It is we mostly use for only straight spur gear. However, it can be used also for helical gear cutting. Now, next the grinding. This grinding is nothing but it is like that, it is like a surface which is presenting the rack, and then it rotates as well as the gears also rotates. These motion they are linked inside the machine by mechanism, and in that way tooth are ground, but the profile is maintained. Now, apart from that, it is also possible we can form the teeth, that is the hot rolling of the teeth that is can be formed. In some cases it may be also cold rolled. Then obviously the casting, where the speed is not much accurate gear also, we can go for casting gears, very slow speed gears, as well as we can go for the milling. In this case we use the form cutter to generate the teeth, and sometimes which is cast teeth, that is also milled after casting. Now, here it is shown that why it is called generating process, because here the cutter is moving, it is rotating as well as it is going and up and down, but while it is moving, this surface is gradually moving to cut the profile, which is practically generating this profile. Okay. Now, if we look into the generating process, then this is the cutter and this is the teeth is being cut. This is moving up and down as well as it is rotating in relation to this gear. That means, suppose here the cutter is having 20 teeth and it is cutting 40 teeth. So, we can consider as if this is a pinion and this is a gear, we have to give this motion between the cutter and this gear blank, and then this cutter move up and down, and this center distance initially it is kept the largest when the cutter is just touching the blank, and gradually it can come inside to up to the root point. Then this is shaping of the internal gear is also done in the same way, keeping this cutter and the gears in a relations, and this cutter moves up and down. It is also possible that we can cut the internal gear by hobbing methods, but that is a special hobbing and we cannot go for very high helix angle for the internal gear, but it is possible. Now, another issue is that measurement of the gears. Gears are manufactured, then how we can know that it has come to the proper shape. First of all, coming to that measurement, we shall consider, you see, this is if we consider a gear teeth uncorrected, in that case this arc tooth thickness is half of the pitch, circular pitch, and the caudal tooth thickness is the straight thickness, and this height from this point to this point is called addendum. This point to here, that means this is called addendum, but the caudal addendum will be more, which is from this line to this line. It can be calculated, that will be shown in the tutorial how this can be calculated. Now, while we are measuring the tooth thickness, one possibility is that we can set a calipers to this height of the teeth here. Say for example, on this we can set the height and then we can measure this distance, but this will not be very accurate. Only during the manufacturing process one can measure this distance, and then he can assess that whether the further cut is given or not, but final measurement is done by measuring the length over teeth. In this case it is shown, this is 3 teeth, okay, and it might be more depending on the, if the gear size is more, minimum 3 teeth is required, and then if the gear size increases, then the number of teeth also increases. But interestingly, if we consider, say, this from this point to this point, this must be base pitch. Similarly, from this point to this point, base pitch. So, this means that if we consider 2 base pitch minus the thickness of the tooth at base, or at one thickness at the base, that will be the total measuring length. So, depending on teeth, and if we know the base pitch, this dimension should be known, because this surface is touching this involute profile here. Okay. So, this will not have the error like measuring at a depth. Next to that, if we would like to measure, now this measurement is also possible that we can put a pin here. We can measure also this teeth by measuring the pin both on the external gear, but in case of internal gear we cannot measure over the teeth what is done in case of external gear, and in that case best method is that putting a roller inside. If we know the equations for the thickness of the tooth at the tangent point, which can be geometrically calculated, then measuring the distance between 2 pin in the opposite sides, we can calculate what will be the thickness of the tooth at a particular radius. Okay. So, that is the measurement techniques. Now, with this brief introduction about the motivation, then I am coming to the course. This course is 8-week course, and in first week this will be on introduction to gear and gear unit design, and next module or next week will be on design of spar, straight and helical gears, bevel and worm gears also. Then module 3, 4, 5 and also 6, this will be devoted on design of a general purpose industrial helical gear reduction unit. First of all, we will design the gear unit, and then we will design the gears, and then we will select the bearing, shaft, and also stage by stage it will be shown how the drawing is developed, and finally it will be shown how the detailed drawings are done and dimensioning is also done. Next, after that, in module 7 we will go for a little bit about the introduction on the involute gear tooth correction, and finally there will be some special topics, internal, epicyclic and other special gearing. Now, as such the references and bibliography is concerned, to develop this course I had to consult many books and many references, but these few are among those which are mostly referred. Apart from that, there are few published papers I have followed, and also there will be some reference books and papers which will be given during the course. There are also some standard which is on gears which has been followed to prepare this course. Now, in the lectures, what the calculations are shown, that as sometimes this is not cross checks, there might have some error somewhere. I believe that it is mostly flawless, but still if it is there, that can be later rectified through the discussion over the forum or from the queries from the participants. So, with this I thank you, and from the next lecture we will go into the detail of the gears.